National Electrical Code, specifically Section 240.10, addresses conductors of different systems occupying the same equipment enclosure. It states that conductors of different systems shall not occupy the same equipment enclosure or be in physical contact outside the enclosure unless otherwise permitted in Article 250. Further clarification is provided in NEC Section 250.145c concerning the installation of feeder conductors of a grounded system and branch circuit feeder or service conductors of an ungrounded system in the same raceway enclosure or cable. It stipulates that conductors of the ungrounded system must be completely enclosed in a metal raceway or cable. This code implies that there is a distinction between grounded and ungrounded systems. The lineman is correct that protected and unprotected conductors, representing feeders and circuits respectively, cannot share a square duct raceway, commonly referred to as a gutter. The NEC mandates the physical isolation of unprotected conductors, which are feeders of an ungrounded system, from protected conductors, which are circuits of a grounded system. The primary reason for this separation is to mitigate the risk of accidental contact between the two distinct electrical systems. Such contact could lead to a short circuit or other electrical hazards, potentially causing damage to equipment or injury to personnel. The disconnect intended for the circuits does not provide adequate protection for the lineman's feeders. The disconnect's function is to safeguard the downstream circuits from overcurrent conditions. It does not protect the feeders from direct contact with protected conductors. The core issue revolves around preventing unintended electrical interaction between systems with different grounding characteristics and protection levels. The segregation ensures that a fault in one system does not propagate to the other, maintaining the integrity and safety of each system. There may be concern regarding induced voltage from the feeders into the circuits. This phenomenon can occur if the feeders are not installed with appropriate separation distance or if the gutter itself lacks adequate bonding. Induced voltage can create undesirable effects, potentially interfering with the operation of sensitive electronic equipment or creating a shock hazard. Good engineering and safety practices dictate that protected and unprotected conductors should be kept separate to minimize the potential for electrical hazards. This separation reduces the probability of accidental contact, induced voltage issues, and fault propagation between different electrical systems. Implementing the separation enhances the overall safety and reliability of the electrical installation. The term protected conductors generally refers to conductors that are part of a circuit that is protected by an overcurrent device, such as a circuit breaker or fuse. These devices are designed to interrupt the flow of current in the event of a fault, preventing damage to the circuit and reducing the risk of fire or electrical shock. In contrast, unprotected conductors typically refer to conductors that are not protected by an overcurrent device. These conductors are often used to supply power to large loads, such as motors or transformers, where the inrush current during startup could exceed the capacity of a standard circuit breaker. The NEC requires that unprotected conductors be installed in a manner that minimizes the risk of accidental contact and that they be properly insulated and grounded. The specific requirements for the installation of unprotected conductors vary depending on the application and the voltage of the circuit. For example, unprotected conductors that are installed in a wet location must be rated for wet locations and must be protected from physical damage. Unprotected conductors that are installed in a hazardous location must be installed in accordance with the requirements of NEC Article 500. Understanding the distinction between protected and unprotected conductors is crucial for ensuring the safety and reliability of electrical systems. By following the NEC requirements for the installation of these conductors, electrical contractors and engineers can minimize the risk of electrical hazards and ensure that electrical systems operate safely and efficiently. Separation distance is a critical factor in preventing induced voltage. The greater the distance between the feeders and the circuits, the lower the induced voltage will be. The NEC specifies minimum separation distances for different types of conductors and applications. These distances are designed to ensure that the induced voltage remains within safe limits. Bonding is another important aspect of minimizing induced voltage. Bonding involves connecting all metal parts of the electrical system to a common ground point. This creates a low impedance path for fault currents, which helps to reduce the voltage potential between different parts of the system. Proper bonding can significantly reduce the risk of electrical shock and equipment damage. The NEC provides detailed requirements for bonding electrical systems. These requirements cover the size and type of bonding conductors, the methods of connecting bonding conductors, and the location of bonding points. In addition to separation distance and bonding, other factors can also contribute to induced voltage. These factors include the length of the conductors, the frequency of the current, and the presence of nearby magnetic fields. Careful consideration of these factors is essential for minimizing induced voltage and ensuring the safe and reliable operation of electrical systems. The NEC is a comprehensive set of standards that covers all aspects of electrical installations. It is updated every 3 years to reflect the latest advances in electrical technology and safety practices. Electrical contractors and engineers should be familiar with the NEC requirements for the installation of protected and unprotected conductors. By following these requirements, they can ensure that electrical systems are installed safely and in compliance with the law. The NEC is not a substitute for sound engineering judgment. Electrical contractors and engineers should always use their best judgment when designing and installing electrical systems. They should also consult with qualified professionals when they have questions or concerns about the NEC requirements. Safe electrical installations are essential for protecting people and property from electrical hazards. By following the NEC requirements and using sound engineering judgment, electrical contractors and engineers can help to ensure that electrical systems are installed safely and reliably. The concept of ungrounded systems also requires further elaboration. An ungrounded electrical system is a type of electrical distribution system that does not have a direct connection to ground. In contrast, a grounded system has one of its conductors intentionally connected to ground, typically at the service entrance. Ungrounded systems are often used in industrial applications where a high degree of reliability is required. The advantage of an ungrounded system is that a single ground fault will not interrupt power to the load. This is because there is no return path for the fault current to flow. However, a second ground fault on a different phase will create a short circuit and interrupt power. Ungrounded systems are typically more expensive to install and maintain than grounded systems. They also require specialized equipment and procedures for fault detection and isolation. The NEC permits the use of ungrounded systems in certain applications, but it also imposes strict requirements for their installation and operation. These requirements are designed to ensure that ungrounded systems are installed safely and do not pose a hazard to personnel or equipment. The decision to use a grounded or ungrounded system depends on the specific application and the requirements for reliability, safety, and cost. Electrical engineers should carefully consider these factors when designing an electrical distribution system. The term raceway refers to any channel that is designed and used expressly for holding wires, cables, or bus bars. Raceways can be made of metal, plastic, or other materials. Examples of raceways include conduits, tubing, and cable trays. Raceways provide physical protection for conductors and help to prevent damage from abrasion, moisture, and other environmental factors. They also provide a neat and organized way to route conductors through a building or facility. The NEC specifies the types of raceways that are permitted for different applications. It also specifies the requirements for the installation of raceways, including the size, support, and grounding of raceways. Proper installation of raceways is essential for ensuring the safety and reliability of electrical systems. Raceways must be properly supported to prevent sagging or damage. They must also be properly grounded to provide a low impedance path for fault current. The size of the raceway must be sufficient to accommodate the number and size of conductors that are installed in it. The NEC provides tables that specify the maximum number of conductors that can be installed in a given size of raceway. The choice of raceway type depends on the specific application and the environmental conditions. For example, rigid metal conduit is often used in industrial applications where conductors are exposed to harsh conditions. Electrical metallic tubing is often used in commercial applications where conductors are not exposed to harsh conditions. Cable trays are often used in large industrial facilities where a large number of conductors need to be routed over long distances. In summary, the lineman's concern is rooted in established electrical safety practices and NEC guidelines designed to prevent hazards arising from mixing conductors of different electrical systems within the same enclosure. The emphasis is on maintaining isolation to avoid potential short circuits, induced voltage issues, and fault propagation, thereby ensuring a safer and more reliable electrical installation. The argument that the disconnect provides sufficient protection is not valid because the disconnect only addresses overcurrent situations and not the fundamental risk of contact between conductors from different systems. Therefore, adherence to the NEC guidelines for physical separation is essential for maintaining electrical safety.